In evaluating limits analytically part 2, we first learn how to find a limit using a conjugate, which we sometimes refer to as the rationalizing technique. If f of x is a rational function containing a radical, and limit as x approaches c of f of x cannot be found directly, then multiply f of x by 1 using the conjugate of either the numerator or denominator over itself. Then simplify this new expression of the function and find the limit. Let's work through these steps using an example where we have to find the limit as x approaches 1 of the quantity 1 minus rad x over the quantity x minus 1. If we tried direct substitution, which is always our first effort, if we put 1 into the numerator, we have 1 minus 1. If we put 1 into the denominator, we have 1 minus 1. This is 0 over 0, which is undefined. So that is our signal that we will need to do some work here. Because the given f of x is a rational function containing a radical, that means we can use this rationalizing technique. So the first step is to multiply f of x by 1 using the conjugate of either the numerator or denominator over itself. The radical appears in the numerator, so we are going to multiply by 1 in the form of 1 plus radical x over itself. Now let's rewrite this limit and get the new expression. So we have limit x approaches 1. Here we have to multiply numerator times numerator, and remember that both of these are binomials. We will be using the rule from algebra that the quantity a minus b times quantity a plus b is equal to a squared minus b squared, and that radical x squared equals x. So this numerator becomes 1 minus x. In the denominator, again, we have two binomials that we have to multiply. Always leave it in its factored form because you're hoping something will cancel. So in this case, we will leave this as quantity x minus 1 times quantity 1 plus rad x. So because we rationalize the numerator, that's our signal to leave the denominator in the factored form, hoping something will cancel. So now we're going to simplify this new expression of the function and then find the limit. So here, this will equal limit as x approaches 1. In the numerator, we have 1 minus x, and in the denominator, we have x minus 1. So now we can use the rule from algebra that says a minus b equals the opposite of the quantity b minus a. So then we can rewrite this numerator as the opposite of the quantity x minus 1. We bring down the denominator, quantity x minus 1 times quantity 1 plus radical x. This is going to equal limit as x approaches 1. Remember, we have to keep writing the limit until we actually perform that limit. Now within the limit, we are allowed to cancel out common factors. So this x minus 1 in the numerator will cancel with the x minus 1 in the denominator, and we are left with negative 1 over 1 plus radical x. Now that we have simplified, we will find the limit of this new simpler expression. So we take this 1, plug it in for x. we can see this is going to become -1 over 1 plus radical 1. And this will simplify to -1/2. And just a reminder, we had to have the limit as x approaches 1 in all of these steps. But once we do the direct substitution, that means we've performed the limit, and that's why we don't write limit in this step or this step. In this example, we have limit as x approaches 3 of quantity x minus 3 over quantity radical x plus 1 minus 2. Now we always try direct substitution first. If we plug 3 into the numerator, we've got 3 minus 3. Plugging 3 into the denominator, we get the square root of 4 minus 2. The numerator simplifies to 0, and so does the denominator, and 0 over 0 is undefined. So now that tells us that we'll have to do some work to rewrite this as a new expression. And because our original expression is a rational function with a radical, we can use the rationalizing technique. We will multiply by 1 in the form of the conjugate of the denominator over itself. So radical x plus 1 plus 2 over radical x plus 1 plus 2. Now this is going to equal the limit as x approaches 3 in the denominator, we have a minus b times a plus b, which of course is going to be a squared minus b squared. So we would get x plus 1 minus 4. Remember that in the numerator, we want to leave that in its factored form because we hope something will cancel. So we will leave this as the quantity x minus 3 times the quantity radical x plus 1 plus 2. Now this is going to simplify. It equals limit as x approaches 3. In the numerator, we have quantity x minus 3 and quantity square root x plus 1 plus 2 over the denominator, which will simplify to be x minus 3. So this will equal limit as x approaches 3. So the next step is to simplify this new expression and find the limit. In the limit, we are allowed to cancel out the common factors, so our expression becomes quantity radical x plus 1 plus 2. Once we simplify, we always try direct substitution next. Once we plug that 3 in, this becomes equal to square root of 4 plus 2, which simplifies to be 4. In this example, we have to find the limit as x goes to 0 of the quantity radical 2 plus x minus radical 2 over x. We try direct substitution first. And if we put a 0 into the numerator, we have radical 2 minus radical 2 over 0 in the denominator. This simplifies to be 0 over 0, which is undefined. Because our original function is a rational expression with a radical in it, we can use the rationalizing technique. So we will need to multiply by 1 using the conjugate of the numerator over itself. So we've got radical 2 plus x plus radical 2 over radical 2 plus x plus radical 2 in the denominator. So this will equal the limit as x approaches 0. In the numerator, we have quantity a minus b times quantity a plus b, which we know will be a squared minus b squared. So radical 2 plus x squared is 2 plus x. We have to subtract radical 2 squared, which is 2. In the denominator, we want to leave this in its factored form because we hope something will cancel. So we've got x times the quantity radical 2 plus x plus radical 2. This is going to equal limit as x goes to 0. In the numerator, we have a 2 here and a minus 2, so those will cancel, and we are left with x. In the denominator, we have x times the quantity square root of 2 plus x plus square root of 2. Now we have to simplify this expression and find the limit. We know that within the limit, we are allowed to cancel the common factors. So this becomes the limit as x goes to 0 of 1 over square root of 2 plus x plus square root of 2. Now we can perform the limit by doing a direct substitution, and we get 1 over radical 2 plus radical 2. Now this is equal to 1 over 2 radical 2. Now we need to rationalize this, so we would multiply by radical 2 over radical 2, and our final result is radical 2 over 4, because this radical 2 times this radical 2 is 2, and 2 times 2 gives us the 4. Next, you will learn about using the squeeze theorem to find limits. First, let's take a look at the squeeze theorem. Assume f of x is less than or equal to g of x is less than or equal to h of x for all values of x near c, except possibly at c. So we exclude c from this requirement. If limit as x approaches c of f of x is equal to the limit as x approaches c of h of x is equal to L, then the limit as x approaches c of g of x equals L. Now let me help you understand what that means. If g of x has to live between f of x and h of x, which is what this picture is saying, g of x is in between h of x on the upper side and f of x on the lower side. If both h of x and f of x have as their limit value at c L, meaning the y value of h of x is approaching L, the y value of f of x is approaching L as x gets closer and closer to c, then the limit as x approaches c of g of x has no choice but to also equal L, because remember, it has to live in between f of x and h of x. Let's take a look at an example. Suppose that negative x squared plus 8x minus 13 is less than or equal to f of x, is less than or equal to x squared minus 8x plus 19 for all x. Find the limit as x approaches 4 of f of x. So since we want to find this limit, and we are given this inequality, which is true for all x, what we can do then is take the limit as x approaches 4 of all three pieces of the inequality. So we would get limit as x approaches 4 of negative x squared plus 8x minus 13 would have to be less than or equal to the limit as x approaches 4 of f of x, which would have to be less than or equal to the limit as x approaches 4 of x squared minus 8x plus 19. So what we did was take the limit as x approaches 4 of all three pieces there. So now let's evaluate the limits. For this first term, we have a polynomial, so we can do direct substitution, and we get negative 4 squared plus 8 times 4 minus 13. And that has to be less than or equal to, now in the middle term here, there's nothing to evaluate, so we bring it down as limit x approaches 4 of f of x is less than or equal to, on this right-hand side term, we have a polynomial, so we can do direct substitution, and we get 4 squared minus 8 times 4 plus 19. So now let's evaluate. We have negative 16 plus 32 is 16. 16 minus 13 is 3. Is less than or equal to limit as x approaches 4 of f of x is less than or equal to 16 minus 32 is negative 16 plus 19 is 3. So notice what's true here. Even though we can't evaluate this limit directly, we know that it has to live between 3 and 3. So therefore, by the squeeze theorem, the limit as x approaches 4 of f of x has to equal 3. So even though we don't know what f of x is, we are able to find the limit as x approaches 4 of f of x, and we know that it has to be 3, because we were told at the beginning that f of x lived between those two functions. So if we're able to find the limit as x approaches 4 of the lower and upper functions, both of them worked out to be the same value, which was 3. So the only possibility for the limit as x approaches 4 of f of x is that it gets squeezed between 3 and 3. So that means the only choice is that it has to equal 3. Next, we learn about two special limits involving sine and cosine. The limit as x approaches 0 of sine of x over x is equal to 1, and the limit as x approaches 0 of 1 minus cosine x over x equals 0. Now a special note, the argument of the trig function, so that would be this x right here, the denominator, which is this x here, and the variable of the limit, which is this x here, must all match exactly in order for these special limit properties to work. So over here, the argument of the trig function, the denominator, and the variable of the limit all have to be the same. Something else to make sure you understand is that sine of x over x does not equal 1. So the expression on its own does not equal 1. It's also important to understand that these special limits only work if the variable of the limit is approaching 0. So if you have the limit as x approaches 1 of sine of x over x, that does not equal 1. Nor if it's limit as x approaches -2, or limit as x approaches pi, or limit as x approaches pi over 6. None of those limits are the special cases here. It's only when you have the limit as x approaches 0 of sine of x over x, now that will equal 1. And just a quick reminder that the variable of the limit, the variable in the denominator, and the variable that is the argument of the trig function must be exactly the same. And the same is true here for this expression. 1 minus cosine of x over x does not equal 0. Or, if the variable of the limit is approaching any other value besides 0, none of those limits give us the special case either. It's only when you take the limit as x approaches 0 of 1 minus cosine x over x, now that will equal 0. So if the expression is missing the limit, then it's not true that it will equal 0. We have to take the limit as x approaches 0 of that expression. This whole entire limit is what equals 0. And a reminder that the variable of the limit, the variable in the denominator, and the variable that is the argument of the trig function, all three of those must be exactly the same. To prove these two special limits, we will use the unit circle and the squeeze theorem. Let's start off with an angle, theta, in quadrant 1. Now, because we're on the unit circle, we know the radius of the circle is 1, so this would be the point 1, 0. Now, for any point on the unit circle, we know the coordinates of that point are going to be x equals cosine theta and y equals sine theta. Now, if we start at the point 1, 0 and draw this dotted vertical line, and we extend the terminal side of theta out until it intersects that dotted line, we know the x-coordinate of that point will be 1, and the y-coordinate will be tangent of theta, and here's why. We know that tangent theta is equal to y over x. Now, at this point right here, we know the x-coordinate is equal to 1, so this is y over 1, which is just y. So what we just found out is that the y-coordinate will equal tangent theta. So that's where that came from. Now what we're going to do is use some geometry. Let's take a look at this big triangle right here and draw its picture here. We know the base is 1 and the height is tangent theta. Now the area of this big triangle can be found by doing 1/2 base times height. So that would be 1/2. The base, we just said, would be 1, and the height would be tangent theta. Now we can say that the area of that triangle will be greater than or equal to the area of this sector which lives inside the triangle. So let's bring that over here. From our trig class, we know that the area of a sector is 1/2 r squared theta. Now r is equal to 1, so we can fill that in, and we bring theta down. We know that the area of that sector will be greater than or equal to the area of a small triangle if we were to connect this point to this point. Let's bring that over here. To find the area of the small triangle, we can use 1/2 base times height. Now the base is 1, so we can fill that in. The height will be the y value of this point right here. And if we relate that back to the original drawing, that's this point here, and the y value is sine of theta. So that means this height is sine theta. And we can go ahead and fill that in. Now let's start to simplify. We notice that all of the terms in this inequality have a 1/2, so let's multiply everything by 2. Then this first term becomes tangent theta. The middle term is theta, and the right-hand term is sine theta. Now let's divide each of those three by sine of theta. Since tangent of theta is just sine theta over cosine theta, if we divide by sine of theta, that's how it ends up equaling 1 over cosine, because the sine here cancels the sine here. All we have left is 1 over cosine theta. The middle term becomes theta over sine theta, and the right-hand side becomes 1, because sine theta over sine theta is 1. Now what we need is actually the reciprocal of this expression. So instead of theta over sine theta, we wish that we had sine theta over theta. So we can take the reciprocal of each piece in the inequality. And remember, when you do that, you have to switch the inequality symbols. And here's why. 1 is greater than 1/2. If I were to take the reciprocal of both sides, the reciprocal of 1 is 1. The reciprocal of 1/2 is 2. Well, we certainly can't bring down the greater than symbol. We would have to switch it. So if you have an inequality and you take the reciprocal of each piece, then you have to switch the inequality symbol. That's how we got from this step to this step. Now we can use this inequality to prove the special limits involving sine and cosine. In this example, prove that the limit as theta goes to 0 of sine theta over theta equals 1. So we start with the inequality we just developed, that cosine theta is less than or equal to sine theta over theta is less than or equal to 1. Now what we want to do is take the limit of each of those pieces. Then it becomes limit as theta goes to 0 of cosine theta is less than or equal to limit as theta goes to 0 of sine theta over theta is less than or equal to the limit as theta goes to 0 of 1. Next, we evaluate the limits. To take the limit of a trig function, we know we will do direct substitution, and the cosine of 0 is equal to 1. This middle limit we are not able to evaluate, so we just bring that down. And on the right-hand side, we're taking the limit as theta goes to 0 of 1, and that's just using the constant rule, so that will equal 1. Even though we can't evaluate this limit directly, we know that it has to live between 1 and 1. So therefore, by the squeeze theorem, the limit as theta goes to 0 of sine theta over theta has to equal 1. And now we've proven that special limit for the sine function. In this example, we have to prove that the limit as theta goes to 0 of 1 minus cosine theta over theta equals 0. Once again, we start with the inequality we developed, that cosine theta is less than or equal to sine theta over theta is less than or equal to 1. Now what we will do is take each of the terms in this inequality and we're going to multiply by sine theta. So now we have cosine theta sine theta less than or equal to sine squared theta over theta less than or equal to sine theta. Next, we will use the Pythagorean identity of sine squared theta plus cosine squared theta equals 1. If we solve that for sine squared theta, then it's equal to 1 minus cosine squared theta. So we do that substitution, and the only thing that will change then is that this middle term becomes 1 minus cosine squared theta over theta. Now the reason we did that is because of what we're trying to prove. We need a 1 minus cosine theta over theta. So we have some work to do to get there, but at least now we have a way to make it happen. Now what we can do is take this 1 minus cosine squared theta and factor it. So it will become 1 minus cosine theta times 1 plus cosine theta. Then what we can do is divide all three terms by 1 plus cosine theta. So now this turns into cosine theta sine theta over 1 plus cosine theta. In this one, the 1 plus cosine theta in the denominator will cancel out, and now we're left with 1 minus cosine theta over theta. And then on the right-hand side, it turns into sine theta over 1 plus cosine theta. And you can see now, for this middle term, we have the expression that we want to take the limit of. So that's what we will do next, is take the limit. So now we've got limit as theta goes to 0, cosine theta sine theta over 1 plus cosine theta, less than or equal to the limit we're trying to prove, which is limit as theta goes to 0, 1 minus cosine theta over theta, will be less than or equal to the limit as theta goes to 0 of sine theta over 1 plus cosine theta. Now in the next step, we just need to evaluate these limits. For this first one, we have trig functions, so we know we can do direct substitution. Cosine of 0 is 1, sine of 0 is 0. In the denominator, we have 1 plus cosine of 0, which is 1. We can't evaluate this limit, so we bring it straight down. And then on the right-hand side, we plug in 0 for theta. Sine of 0 is 0. Cosine of 0 is 1. Now simplifying, we get that 0 is less than or equal to limit as theta goes to 0 of 1 minus cosine theta over theta is less than or equal to 0. So even though we can't evaluate this limit directly, we know that it has to be between 0 and 0. So therefore, by the squeeze theorem, limit as theta goes to 0 of 1 minus cosine theta over theta is equal to 0. Now we've proven both of these special limits, and we can use them to help us evaluate other limits. In this example, we have to evaluate the limit as x goes to 0 of sine 5x over x. Now, in order to use the special limit that we just learned about, we need the argument of the trig function, the denominator, and the variable of the limit all to match each other exactly. Now, there's nothing we can do to change the argument of the sine function here. Remember that 5 cannot be factored out. That has to stay there. So then what we can do is work on changing this denominator. So we're going to start off by multiplying by 1 in the form of 5 over 5. Now this will become the limit as x approaches 0 of 5 sine of 5x over 5x. So now we have the argument of the trig function matching the denominator. But now remember, to apply the rule, we still need the variable of the limit to match, and the numerator needs to be just the sine function. Now, the scalar multiple rule tells us that this 5 can come out front. So that means we can rewrite this as 5 times the limit as x goes to 0 of sine 5x over 5x. So now we are almost there. We have the argument of the trig function matching the denominator. The only thing we need is for the variable of the limit to be the same thing. So all three of these must match. So here's what we can do. Let y equal 5x. Now as x goes to 0, certainly 5x will also go to 0. And since y is just 5x, that means we can say y goes to 0. So then we can rewrite this limit as 5 times the limit as y goes to 0 of sine y over y. Now we have all three pieces matching each other exactly, which is what we need. And now we can apply this rule. So this will equal 5 times this limit right here is exactly equal to 1. And so our result is 5. In this example, we have to evaluate the limit as x goes to 0 of tangent x over x. Now, neither one of our two special limits involves a tangent function. So what we will want to do is use trig identities to see if we can turn this tangent x into one of the trig functions that we can evaluate. So this is going to equal the limit as x goes to 0 tangent of x can be written as sine of x over cosine of x. We bring over our denominator of x. And remember, if you have something in the form of a over b over c, that's the same thing as a over b times 1 over c, which is a over b times c. So when you have a rational expression in this form, you can immediately write it in this form. So then in our case, we will have the limit as x goes to 0 of sine of x over x cosine x. Now what we can do is split this up into two limits. Because remember, the product rule says that the limit of a product is the product of the limits. So this would become the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of 1 over cosine x. Remember that cosine x was in the denominator, so when we separate this into sine x over x, then the other piece has to be 1 over cosine x. Now, this first limit is exactly matching our rule because the argument of the trig function, the denominator, and the variable of the limit all match, and we have sine of x isolated in the numerator. So this limit is exactly equal to 1. Now we will need to multiply that times this limit. It has a constant of 1 in the numerator. In the denominator, we have a trig function, which means we will evaluate the limit with direct substitution, and cosine of 0 is equal to 1. So now we have 1 times 1 over 1, which of course simplifies to 1. In this example, we have to evaluate the limit as theta goes to 0 of the quantity 1 minus cosine theta over 2 over 3 theta. We can tell that it's going to be this special limit, and so now we just need to make it so that the argument of the trig function, the denominator, and the variable of the limit all match each other. The first thing we notice is that we can use the scalar multiple rule to bring this 3 that's in the denominator out front. So this is going to equal 1/3 times the limit as theta goes to 0 of 1 minus cosine theta over 2 over theta. Now remember, there's nothing we can do to get the argument of the trig function to be anything other than theta over 2. Cosine of theta over 2 does not equal 1/2 cosine theta. That will never happen, so be careful to avoid that error. So what we have to do is get this denominator to match the argument of the trig function. And in order to do that, we will multiply by 1 in the form of 1/2 over itself. So this is going to equal 1/3 times the limit as theta goes to 0. And now we can go ahead and apply the rule for the scalar multiple and bring this 1/2 out front. Then on the inside, in the numerator, we will have 1 minus cosine of theta over 2. And in the denominator, we have theta over 2. So now our denominator matches the argument of the trig function, and we just need to get the variable of the limit to match as well. So we can come off to the side and say let x equal theta over 2. as theta goes to 0, theta over 2 will also go to 0. And since x is just theta over 2, we can say, therefore, x would go to 0. So then this will become equal to 1/6 limit as x goes to 0 of 1 minus cosine x over x. Now this is exactly the rule that we need. So this will equal 1/6. And remember that it's this entire limit that's going to equal 0. And 1/6 times 0 is equal to 0. Now, something to be very careful of when you're showing your work for these limits is that you show the step where you have the special limit formatted exactly as it needs to be formatted. Then you show the step where you plug in the value for that special limit. Then, finally, you simplify to get your result. In this example, we have to do the limit as a goes to 0 of the quantity 1 minus cosine squared a over a. Now, in this case, you need to be careful to notice that this is not the special limit because we have that cosine squared in there. So we can rewrite this as the limit as a goes to 0. And in the numerator, we can use a Pythagorean identity and replace 1 minus cosine squared a with sine squared of a. In the denominator, we bring over the a. Now we can use the rule that the limit of a product is the product of the limits, because really what we have here is the limit as a goes to 0 of sine of a over a times sine of a. Now this is equal to limit as a goes to 0 of sine of a over a times limit as a goes to 0 of sine of a. Now this is going to equal, this first limit is one of the special limits, and we know that equals 1, times this second limit, because it's a trig function, we can do a direct substitution and plug 0 in for a. The sine of 0 is equal to 0. So this whole limit ends up equaling 0. Now, an alternate way to solve this one would be to factor out the 1 minus cosine squared a into 1 minus cosine a times 1 plus cosine a. And you can see that this limit works out to the same result.